Look at your hand. Not quickly, slowly. The way you might look at something you have never seen before. The knuckles, the tendons moving beneath the skin when you flex the fingers, the lines crossing the palm like a map of somewhere you have never been. The opposable thumb, sitting apart from the others, capable of meeting each fingertip with a precision that no other creature on Earth can fully replicate. This hand is approximately 200,000 years old. Not this specific hand, but the design of it. The blueprint. The particular arrangement of bones and muscles and nerves that makes it what it is has been stable, more or less, for roughly 200 millennia. Every hand that built a fire, carved a flute, wrote a letter, held a child, reached toward another person in the dark, they were all this hand. The same design, repeated across 200,000 years of human life. But the hand itself is not the beginning of the story. The hand is the recent part. Go back further. Past the first humans, past the species that came before them, past the long chain of ancestors whose faces we cannot reconstruct and whose names we will never know. Go back to the moment, somewhere in the deep African past, in a landscape that no longer exists, when the lineage that would eventually produce you first separated from the lineage that would produce our closest living relatives. Go back to the forests and the grasslands and the long slow pressures of climate and time that shaped the body and the brain and the behavior of the creature that would, eventually, look at its own hand and wonder where it came from. That is where this story begins. Not with civilization, not with language, not with the first city or the first written word. With something older and stranger and more improbable than any of those things, the fact that we exist at all. The fact that the particular chain of events, the extinctions and migrations and adaptations and accidents that produced the human species happened in exactly the way it did, and not in any of the infinite other ways it might have gone. You are the result of an almost incomprehensible sequence of unlikely events, each one necessary for the next, stretching back not thousands but millions of years. Get comfortable. Let's begin. The split between the lineage that would become humans and the lineage that would become chimpanzees occurred somewhere between 6 and 7 million years ago. This is not a guess. It is a figure derived from multiple independent lines of evidence, the fossil record, the comparative anatomy of living species, and most precisely, the molecular clock, the rate at which DNA accumulates mutations over time. By comparing the genomes of humans and chimpanzees and counting the differences, geneticists can calculate approximately when the two lineages last shared a common ancestor. That ancestor was not a chimpanzee. It was not a human. It was something else entirely, a creature for which we have very limited fossil evidence and no agreed name, living in the forests and woodland margins of what is now sub-Saharan Africa, in a world that had no ice caps at the poles, where the climate was warmer and wetter than today, and where the continent of Africa looked nothing like it does now. We share approximately 98.7% of our DNA with chimpanzees. The 1.3% difference is responsible for language, art, mathematics, cities, music, war, agriculture, and every other thing that distinguishes human life from the life of our closest relatives. The distance between a human being and a chimpanzee, measured in genetic terms, is smaller than the distance between some species of birds that look nearly identical to each other. The 1.3% is everything. And it took 6 million years to accumulate. The oldest known member of the human family, the group of species more closely related to us than to chimpanzees, known as hominins, may be a creature called Sahelanthropus cadensis, discovered in Chad in 2001. It lived approximately 7 million years ago. It is known from a single skull, nicknamed Tumai, meaning hope of life in the local Goran language. What makes Tumai significant and controversial is the position of the foramen magnum, the hole at the base of the skull through which the spinal cord passes. In four-legged animals, this opening faces backward. In upright walking animals, it faces downward, because the spine rises vertically beneath the skull rather than extending horizontally behind it. Tumai's foramen magnum appears to face downward, suggesting that this creature, 7 million years ago, may already have been walking upright or at least more upright than a chimpanzee. If this interpretation is correct, it pushes the origin of bipedalism, walking on two legs, the characteristic that most clearly distinguishes hominins from other apes, back further than many researchers had previously believed. It suggests that upright walking may have been the first major adaptation that separated our lineage from that of the other apes, predating the enlargement of the brain by millions of years. We walked before we thought. The body came before the mind. For most of the 20th century, scientists believed that human evolution was a relatively straightforward progression, a ladder of improvement leading from primitive ape-like ancestors through increasingly sophisticated intermediate forms to modern humans at the top. This image, sometimes called the March of Progress, made famous by a 1965 illustration showing a sequence of figures walking from left to right in increasing uprightness, is almost entirely wrong. Human evolution was not a ladder. It was a bush. At various points in the past, multiple different hominin species existed simultaneously, walking the same landscapes, eating similar foods, possibly encountering one another, before most of them went extinct. The fossil record now contains the remains of more than 20 distinct hominin species, all of them evolutionary experiments, most of them dead ends. We are not the pinnacle of a directed progression. We are the sole survivor of a large and diverse family, almost all of whose members are gone. At various points in the last 3 million years, there were multiple human-like species alive on Earth at the same time. The world has had only one hominin species, us, for a relatively brief period. The solitude of our species is historically unusual. It is not the natural condition of the human family. It is the outcome of a long series of extinctions. Australopithecus, the group of hominin species that lived in Africa between roughly 4 and 2 million years ago, walked upright but had brains not significantly larger than those of modern chimpanzees. The most famous member of this group is a partial skeleton discovered in Ethiopia in 1974. Officially designated AL 288-1 and nicknamed Lucy. She was a female Australopithecus afarensis who lived approximately 3.2 million years ago, stood roughly 3.5 feet tall, and weighed perhaps 60 pounds. Lucy walked upright, her knee joint and the angle of her femur make this clear, but she also retained features suited to climbing trees, long arms, curved fingers, a body plan that suggests she spent significant time on the branches as well as on the ground. She represents a genuinely transitional stage that the old ladder model of evolution had difficulty accommodating, a creature combining capabilities from two different modes of life. She was discovered by a team led by Donald Johanson, who named her after the Beatles' song playing on a tape recorder in the camp on the evening of the discovery. The oldest known member of the human family tree to have a popular name owes it to a song released 9 years before she was found, by a band from a country that did not exist when she was alive, recorded in a medium she would have been entirely incapable of comprehending. The development of stone tool technology, the deliberate shaping of rocks to create cutting edges, marks one of the most significant thresholds in hominin prehistory. The oldest known stone tools, found at a site called Lomekwi 3 in Kenya, date to approximately 3.3 million years ago. They predate the genus Homo, the group that includes modern humans and our most recent ancestors, by at least 500,000 years. This means that stone tool use began not with humans but with an earlier hominin, possibly Australopithecus or a closely related species. For a long time, tool use was considered the defining characteristic of humanity, the behavior that set our lineage apart from all others. The discovery that tools predate the human genus by hundreds of thousands of years complicated this significantly. And the subsequent discovery that chimpanzees, crows, and several other species also use and sometimes modify tools complicated it further. What stone tools did for early hominins was expand the range of food available to them. A sharp stone flake can cut through hide and access the meat and marrow of large animals, resources previously inaccessible to creatures without claws or large canine teeth. Access to high-protein, high-fat food from large carcasses is one of the factors researchers believe drove the expansion of the hominin brain over the following millions of years. The hand that first struck one rock against another to produce a cutting edge was doing something that would, in time, lead to every subsequent technology in human history. It did not know this. It was hungry. Fire, the controlled use of flame for warmth, light, protection, and cooking, transformed the human body as well as human behavior. The earliest convincing evidence of controlled fire use by hominins comes from a site called Wonderwork Cave in South Africa, dating to approximately 1 million years ago. Earlier sites suggest possible fire use going back 1.5 million years, though the evidence is more ambiguous. The anthropologist Richard Wrangham has argued that cooking, the application of heat to food, was the decisive catalyst for the dramatic increase in brain size seen in the genus Homo beginning around 1.8 million years ago. Cooking breaks down the cellular structure of food, making it significantly easier to digest and dramatically increasing the caloric return per unit of food consumed. A cooked diet requires less time and energy to chew and process than a raw one. The consequences for human anatomy were profound. As cooking improved the efficiency of digestion, the long gut required by raw food diets could shrink, freeing metabolic energy for other uses. The large jaw muscles and heavy facial architecture needed for extensive chewing of raw food could reduce, changing the shape of the skull and allowing the brain case to expand. We are, in a very literal sense, shaped by fire. The large brain in the skull, the small jaw beneath it, the relatively short digestive tract, all of these are, at least in part, the body's adaptation to a cooked diet. We have been cooking for so long that our bodies have reorganized themselves around the assumption that the food will be heated before it arrives. Homo erectus, the hominin species that first left Africa and spread across much of the Old World, was arguably the most successful member of the human family in terms of geographic range and duration. It appeared in Africa approximately 1.9 million years ago and survived, in some populations, until perhaps 100,000 years ago, a span of nearly 2 million years. By comparison, our own species, Homo sapiens, has existed for roughly 300,000 years. We are, by the measure of duration, a young and as yet unproven experiment. Homo erectus reached the Caucasus by 1.8 million years ago, Java by approximately 1.5 million years ago, and China by at least 1.1 million years ago. It accomplished this expansion without boats, without maps, without any form of deliberate long-distance planning as we would understand it. The movement was gradual, populations expanding into new territories over generations, following food and water, never aware that they were doing anything that would later be called migration. The body of Homo erectus was, in many ways, more similar to ours than to that of earlier hominins. Taller, with longer legs suited to distance walking, a reduced size difference between males and females, and a brain roughly 3/4 the size of a modern human brain. It was a creature built for covering ground, for the long, persistent, tireless movement across open landscapes that characterizes human locomotion to this day. The Neanderthals, Homo neanderthalensis, were not the brutish, stooped, dim-witted creatures of popular imagination. They had brains, on average, slightly larger than our own. They buried their dead. They used ochre pigment, possibly for body decoration. They made jewelry from eagle talons and shells. They cared for injured and elderly members of their groups, individuals who could not have survived without sustained assistance from others, individuals whose survival required deliberate choice. Neanderthals lived in Europe and Western Asia for approximately 400,000 years before modern humans arrived. They survived ice ages, hunted large game, and adapted to environmental conditions of considerable severity. Their extinction, which occurred roughly 40,000 years ago, was not the inevitable failure of an inferior species. It was the end of a long and successful lineage, occurring in the context of competition and contact with a new arrival. That new arrival was us. The precise relationship between the extinction of the Neanderthals and the arrival of modern humans in Europe is still debated. Direct violence, disease, competition for resources, and reproductive absorption into the modern human population have all been proposed as contributing factors. What the genomic evidence makes clear is that the relationship was not purely hostile. Most people of non-African ancestry today carry between 1 and 4% Neanderthal DNA, inherited from interbreeding that occurred tens of thousands of years ago. The Neanderthals are not entirely gone. They are distributed in small fractions across the genomes of most people alive today. Modern humans, Homo sapiens, first appear in the fossil record in Africa approximately 300,000 years ago, at a site called Jebel Irhoud in Morocco. This date, established by thermoluminescence dating of burnt flint tools found with the fossils, pushed back the known origin of our species by roughly 100,000 years when it was announced in 2017. It also shifted the perceived center of human origins. Jebel Irhoud is in North Africa, far from the East African sites Ethiopia, Kenya, Tanzania that had previously been considered the exclusive cradle of humanity. The emerging picture is that Homo sapiens did not originate in a single place and then spread outward. It may have emerged across a large portion of the African continent simultaneously, through a network of populations that were geographically separated but periodically connected by the movement of individuals and genes. Africa, in this model, was not a single birthplace but a vast evolutionary laboratory, populations adapting to different local environments, exchanging genetic material during periods when climate allowed movement, slowly accumulating the combination of physical and cognitive traits that would eventually constitute our species. The origin of humanity was not an event. It was a process extended across a continent, across hundreds of thousands of years, in populations that did not know they were becoming something new. The human brain is the most complex object known to exist in the universe. It contains approximately 86 billion neurons. Each neuron can form connections, synapses, with thousands of other neurons. The total number of synaptic connections in a single human brain is estimated at roughly 100 trillion. The number of possible states this network can occupy exceeds the number of atoms in the observable universe. This object grew to its current size over a period of approximately 3 million years, from the chimpanzee-sized brain of early Australopithecus to the modern human brain. The rate of increase was not constant. There appear to have been periods of rapid expansion separated by longer plateaus. The most dramatic period of brain expansion occurred between roughly 800,000 and 200,000 years ago. What drove this expansion is still debated. Diet, social complexity, tool use, language, climate variability, all have been proposed as selective pressures. The most persuasive current accounts suggest that it was not a single driver but a feedback loop. Larger brains enabled more complex social behavior, which placed greater demands on the brain, which selected for further expansion, which enabled more complex behavior still. The brain built the social world. The social world built the brain. They made each other, in a loop that ran for millions of years, and the result is the object behind your eyes, the thing reading these words, right now, wondering about itself. Language, the capacity to communicate through a system of arbitrary symbols combined according to rules to produce unlimited meanings, is one of the most debated topics in the study of human origins. The debate is not about whether language is important. It is about when it began, how it evolved, and whether it appeared suddenly or gradually. Some researchers believe that full human language capacity arose relatively recently, perhaps 70,000 to 100,000 years ago, as part of a broader cognitive revolution that also produced art, complex tools, and long-distance trade. Others believe the roots of language extend much further back, developing incrementally over hundreds of thousands of years. The fossil record cannot directly answer this question. Soft tissue does not preserve. The brain structures associated with language production leave faint impressions on the inner surface of the skull, and these impressions suggest that some precursors to modern language capacity may have been present in Homo erectus and earlier ancestors. What language gave humanity was not merely communication other animals communicate, but the ability to communicate about things that are absent, hypothetical, past, and future. To say not just danger here now, but last season, in the valley to the east, there was danger of a particular kind, and here is how we responded, and here is what we should do differently next time. Language is a technology for transmitting experience across time. It is the reason that every human generation does not have to begin again from scratch. The hyoid bone, a small, horseshoe-shaped bone in the throat that anchors the muscles of the tongue and larynx, is the only bone in the human body not connected to any other bone. It floats, suspended entirely by muscles and ligaments, and it is essential to the production of complex speech. Without a hyoid positioned as it is in modern humans, the range of sounds the throat can produce is significantly limited. A hyoid bone was found in 1989 at the Kabra cave in Israel, belonging to a Neanderthal who lived approximately 60,000 years ago. Its shape and position were virtually identical to the hyoid of a modern human. This was one of the first pieces of physical evidence suggesting that Neanderthals may have had some capacity for speech, not necessarily the full range of modern human language, but something more than grunts and calls. The hyoid cannot tell us what was said. It can only tell us that the physical infrastructure for saying it was in place. A Neanderthal standing in a cave 60,000 years ago had a throat arranged, at least in part, for speech. Whether words came out of it, and if so, what they meant, is a question that no amount of fossil evidence will ever fully answer. The bone that makes human language physically possible is the one bone that leaves no impression on any other bone. It is found only when conditions are exactly right for its preservation. Most of the time, it simply disappears. The out-of-Africa hypothesis, the theory that all living humans descend from a population that left Africa within the last 100,000 years, is supported by an overwhelming convergence of genetic, fossil, and archaeological evidence. The genetic evidence is particularly compelling. When researchers analyze the DNA of living human populations from around the world, they find that African populations contain more genetic diversity than all non-African populations combined. This is exactly what the out-of-Africa model predicts. The founding population that left Africa carried only a subset of the genetic variation present on the continent, and all subsequent human diversity outside Africa descends from that subset. The estimated time of departure varies by study and methodology, but the most widely accepted range places the major dispersal event between 60,000 and 70,000 years ago. Within a remarkably short time in geological terms, the descendants of this founding population reached South Asia, Southeast Asia, and Australia. Australia was reached by at least 65,000 years ago, which means that the first Australians crossed open water to reach a continent they had never seen, using watercraft sophisticated enough to make an ocean crossing, at a time when the entire non-African human population may have numbered in the tens of thousands. The courage, or the curiosity, or the desperation required for that crossing is not something the fossil record can measure. But it happened. The population of modern humans came extraordinarily close to extinction approximately 70,000 years ago. The Toba catastrophe theory proposes that a massive volcanic eruption on the island of Sumatra, the largest known volcanic event in the last 2 million years, triggered a volcanic winter that lasted years and dramatically reduced global temperatures. The evidence for a severe population bottleneck in human genetics around this time suggests that the global human population may have been reduced to somewhere between 3,000 and 10,000 individuals. If the bottleneck was real and as severe as some estimates suggest, then every human being alive today descends from a population smaller than the current population of a small town. The genetic diversity of our entire species, the full range of variation that distinguishes one person from another across the entire planet, descends from a group of survivors small enough to fit in a single modern sports stadium. The Toba hypothesis remains debated. Some researchers question whether the volcanic winter was as severe as proposed, and some African archaeological sites show apparent cultural continuity through the period in question. But even the conservative estimates suggest that our species has lived close to the edge. The line of descent that connects every living human being to the deep past is thinner and more improbable than it appears from the vantage point of 8 billion people. The colonization of Australia by modern humans, at least 65,000 years ago, and possibly earlier, required crossing a minimum of 90 kilometers of open ocean, out of sight of land. This was not accidental. The crossing of open water out of sight of any shore cannot happen by drifting. It requires a boat or a raft capable of intentional navigation. It requires the knowledge that land exists on the other side. It requires a decision made in advance, with preparation, by a group of people who understood enough about the sea to commit themselves to it. The people who made this crossing left no written record. Their boats have not survived. We know they existed only because their descendants were there on a continent that could not otherwise have been reached when the first European ships arrived tens of thousands of years later. What the Australian colonization demonstrates is that the behavioral and cognitive modernity of the humans who left Africa was already complete by 65,000 years ago. These were not primitive or proto-human beings. They were people fully capable of complex planning, of building watercraft, of organizing a crossing, of establishing themselves in an entirely new environment and thriving there for tens of thousands of years before anyone from the rest of the world arrived. The Aboriginal Australians are the descendants of the most successful long-distance colonization in human prehistory. Their culture, maintained continuously for at least 65,000 years, is the oldest continuous human culture on Earth. The Denisovans, a hominin group known almost entirely from DNA extracted from a few small bone fragments found in a Siberian cave, are one of the most remarkable discoveries in the history of paleoanthropology. In 2010, researchers extracted DNA from a fingerbone found in Denisova Cave in the Altai Mountains of Siberia. The DNA was neither modern human nor Neanderthal. It belonged to a previously unknown hominin group, one that had been genetically isolated from both Neanderthals and modern humans for hundreds of thousands of years. The physical evidence for Denisovans remains extraordinarily sparse: a few teeth, a fingerbone, a partial lower jaw found in Tibet. But their genetic legacy is substantial. Modern populations in Papua New Guinea and other parts of Oceania carry between 4 and 6% Denisovan DNA. Tibetan populations carry a specific Denisovan gene variant EPAS1 that helps the body cope with low oxygen levels at high altitude. It was inherited from Denisovans and is the reason Tibetans can live comfortably at elevations that would incapacitate most people. The Denisovans remain a ghost lineage known almost entirely through the traces they left in the genomes of living people rather than through physical remains. An entire branch of the human family is known to us primarily through DNA. They have no face in the fossil record. But their genes are alive today, helping people breathe on the roof of the world. The first anatomically modern humans to reach Europe arrived approximately 45,000 years ago and encountered a continent already occupied by Neanderthals who had lived there for hundreds of thousands of years. What followed was not, as far as the evidence suggests, a swift conquest. The process by which Neanderthals disappeared and modern humans replaced them took approximately 5,000 years, a long and gradual transition during which the two groups coexisted, occasionally interbred, and possibly competed for the same resources without direct organized conflict. The modern humans who arrived in Europe brought with them a behavioral repertoire that included long-distance trade networks, personal ornamentation, and a proliferation of symbolic and artistic expression that had not previously been present in European material culture at the same scale. Whether this cultural difference gave modern humans a decisive competitive advantage, or whether the Neanderthal extinction was more a matter of demographic mathematics, a slightly lower birth rate, a slightly higher mortality rate, compounded over millennia, is still debated. What is not debated is the outcome. By approximately 40,000 years ago, the Neanderthals were gone. The human family, which had for most of its history been populated by multiple simultaneous species, was reduced to one. that reduction has never been reversed. We have been alone, as a genus, ever since. The oldest undisputed figurative art images of recognizable animals made with deliberate representational intent dates to approximately 45,000 years ago in the caves of Sulawesi, Indonesia. This is significant not only for its age but for its location. For a long time, the oldest cave art was believed to be in Europe, the famous painted caves of Lascaux, Altamira, and Chauvet. The discovery that art of equal or greater age exists in Southeast Asia suggests that the capacity for symbolic and representational thinking arrived with the first modern humans who left Africa and was not developed independently in Europe. The Sulawesi art includes images of local animals, babirusa, a pig deer native to the island, and hand stencils made by placing a hand against the cave wall and blowing pigment around it. The hand stencil is one of the most persistent and widespread images in all of prehistoric art, appearing on every inhabited continent. It is the oldest self-portrait in human history, not a representation of the face, but of the hand, the tool-using, world-shaping hand that distinguishes the human body from every other. Someone, 45,000 years ago, pressed their hand against a cave wall in Sulawesi and blew red ochre around it. They left an image that said, in the simplest possible terms, "I was here. A hand was here." This is what it looked like. The Venus figurines, small portable sculptures of female figures found across a vast geographic range from Western Europe to Siberia, represent some of the oldest known examples of sculptural art. The oldest, the Venus of Hohlfels, was found in the same German cave system that produced the oldest known bone flute. It dates to approximately 35,000 to 40,000 years ago and was carved from mammoth ivory. It depicts a female figure with exaggerated reproductive features, large breasts, wide hips, prominent abdomen, and no facial features. Where the head would be, there is instead a carved ring, suggesting the figure may have been worn as a pendant. Over 200 Venus figurines have been found across Europe and parts of Asia, spanning a period of roughly 25,000 years. They are remarkably consistent in their stylistic choices, the exaggerated reproductive anatomy, the frequent absence of facial features, the small scale suited to being held or carried, despite being produced by populations separated by thousands of kilometers and thousands of years. What they meant to the people who made them is unknown. They have been interpreted as fertility symbols, as representations of goddesses, as self-portraits made by women looking down at their own bodies, as instructional objects, as artistic explorations. The consistency of the form across such vast distances and times suggests that something specific was being communicated. But the content of that communication is irretrievably lost. The figurines remain small, heavy, smooth from handling. Objects made to be touched. The ochre, the iron-rich red and yellow pigment used by early modern humans for body decoration, cave painting, and ritual purposes, appears in the archaeological record far earlier than any art made with it. At Pinnacle Point in South Africa, archaeologists have found evidence of ochre use dating back 164,000 years. The ochre had been ground and processed, deliberately prepared for use long before any surviving painting or sculpture. This is one of the pieces of evidence suggesting that modern human behavior, symbolic thinking, the use of materials for purposes beyond the purely practical, developed gradually over hundreds of thousands of years, not in a sudden burst. Red ochre in particular holds a striking place in early human prehistory. It was placed in graves alongside the dead across a vast range of cultures and time periods. It was used to paint the bodies of the living and the faces of the dead. In some Neanderthal burial sites, ochre has been found associated with skeletal remains, suggesting that the practice of coloring the dead, of marking them with the color of blood and life as they were returned to the earth, may predate our own species. The color red was the first color used deliberately by human beings. The choice was not random. It was the color of the body's interior, of what keeps things alive when it stays inside, and marks the end of life when it flows out. The first human art was painted in the color of blood. Persistence hunting, the practice of pursuing prey over long distances until the animal collapses from heat exhaustion, is believed by many researchers to be one of the oldest and most distinctively human hunting strategies. Most mammals, including the large prey animals of the African savanna, are faster than humans over short distances but cannot maintain high speed for extended periods without overheating. Their primary cooling mechanism, panting, requires them to slow their breathing, which means they must slow or stop running to cool down. Humans, uniquely among large mammals, can cool while running, through the combination of sweating and upright posture that exposes the body's surface to airflow. A human hunter pursuing a large antelope or wildebeest across open grassland at midday is engaged in a physiological contest. The animal is faster. But the human can run through the heat of the day without stopping, tracking the prey, maintaining pressure, not allowing it time to recover. Eventually the animal collapses. This strategy requires endurance, heat tolerance, and the ability to track, to follow signs left by an animal that is no longer visible, to predict where it has gone, to hold the idea of the prey in mind over hours of pursuit. It requires, in other words, a kind of thinking about invisible things, a model of where the animal is, based on evidence rather than direct perception. Some researchers believe that persistence hunting shaped the human body and the human mind simultaneously, that the demands of the long chase selected for the endurance physiology and the predictive cognition that distinguish us from every other primate. The development of agriculture, the deliberate cultivation of plants and the domestication of animals as a primary food strategy is often described as the most important transition in human history. It began independently in at least 11 different locations around the world, starting approximately 12,000 years ago in the Fertile Crescent of the Middle East. Wheat, barley, lentils, and peas were the first cultivated crops. Sheep, goats, cattle, and pigs were the first domesticated livestock. Within a few thousand years, similar processes had begun in China with rice and millet, in Mesoamerica with maize, in the Andes with potatoes and quinoa, in sub-Saharan Africa with sorghum and millet. Agriculture made it possible to feed far larger populations from a given area of land than hunting and gathering could support. It made possible the accumulation of food surplus, and with surplus came storage, and with storage came the need to track and defend what was stored, and with that came accounting, property, inequality, hierarchy, and eventually the state. What agriculture also brought, and this is less often discussed, was a dramatic reduction in the average quality of human life for the first several thousand years of its practice. Compared to hunter-gatherers, early agricultural populations were shorter, had worse teeth, suffered from more nutritional deficiencies, worked longer hours, and were more vulnerable to epidemic disease. Humanity chose agriculture not because it was better for individuals, but because it produced more people. It was not progress by any individual measure. It was success by the only measure evolution recognizes. The domestication of the dog, the transformation of wolves into the animal that shares human homes today, is the oldest known domestication of any species, predating agriculture by thousands of years. Genetic evidence suggests that dogs were domesticated from wolves somewhere between 15,000 and 40,000 years ago, though the precise timing and location remain subjects of active debate. What is clear is that the domestication occurred before the development of settled agricultural communities, meaning that the first domestic dogs lived with nomadic hunter-gatherers, not farmers. The process by which wolves became dogs is still not fully understood. The most widely accepted model suggests that wolves that were less fearful of humans, that could tolerate proximity to human campsites without fleeing, gained access to the food scraps and waste that human camps produced. Over generations, the less fearful wolves bred with each other, and their offspring became gradually less fearful still, until a population existed that not only tolerated humans but actively sought their company. What happened next? The development of the specific bond between dogs and humans, the extraordinary sensitivity of dogs to human social cues, the ability of a dog to follow a human pointing gesture that even chimpanzees struggle with, may be the most remarkable interspecies relationship in the history of life on Earth. Two predators, from entirely different evolutionary lineages, learn to read each other's faces and cooperate across the boundary of species. The dog was the first being, outside our own family, that humanity learned to love. The last of the non-modern human species to go extinct was almost certainly Homo floresiensis, a small-bodied hominin found on the Indonesian island of Flores, nicknamed the Hobbit by the researchers who discovered it. Homo floresiensis stood approximately 3.5 feet tall and had a brain roughly the size of a grapefruit, smaller than that of Homo erectus and comparable in volume to that of Australopithecus. And yet it made stone tools, hunted pygmy elephants, and appears to have controlled fire. It survived on Flores until approximately 50,000 years ago, meaning it was alive at the same time as anatomically modern humans who were by then present in Southeast Asia. Its small size is believed to be the result of island dwarfism, a well-documented evolutionary phenomenon in which large-bodied animals isolated on islands with limited resources evolved towards smaller body size over generations. The discovery of Homo floresiensis in 2003 was genuinely shocking to the scientific community, not because small hominins were theoretically impossible, but because they had survived so recently, so close to modern human populations, with such a small brain, and apparently with sufficient intelligence to hunt and use fire and make tools. It raised questions that have never been fully resolved about the relationship between brain size and cognitive capacity, and about what, exactly, it means to be human. Intelligence, the Hobbit quietly suggested, may not scale as simply as we assumed. The genetic evidence for human prehistory extracted from ancient bones and teeth, from permafrost and cave sediments, from the DNA of living people around the world, has revolutionized our understanding of human origins more dramatically in the past 2 decades than the previous 2 centuries of fossil discovery. Ancient DNA analysis has revealed that the history of human populations is one of constant movement, mixture, and replacement. Populations that genetic and archaeological evidence suggested had been in place for thousands of years were found, upon analysis of ancient genomes, to have been largely replaced by incoming groups. The people who built Stonehenge were largely replaced by the Bell-Beaker people who arrived from Central Asia a few centuries later. The hunter-gatherers of pre-agricultural Europe were largely replaced by incoming farmers from Anatolia. Those farmers were in turn mixed with incoming steppe pastoralists. The story of where any given population came from is, in almost every case studied so far, more complicated, more layered, and more mobile than anyone expected. Humans have always moved. They have always mixed. The boundaries that feel fixed, national, ethnic, regional, are overlaid on a substrate of constant ancient movement that makes all such boundaries, in genetic terms, relatively recent and relatively thin. The ancient DNA evidence has revealed that human difference is real, important, and far more dynamic and fluid in its origins than any static model of fixed populations could accommodate. The Y chromosome, the genetic element passed from father to son, used to trace patrilineal descent through deep time, reveals a remarkable bottleneck in human history approximately 5,000 to 7,000 years ago. During this period, the genetic diversity of the Y chromosome collapsed dramatically. Statistical modeling of the genomes of living men suggests that the ratio of breeding men to breeding women fell to as low as 1 to 17, meaning that for every 17 women who passed their genes to subsequent generations, only 1 man did. The cause of this bottleneck is not certain. The most widely discussed hypothesis is that it reflects a period of intense intergroup conflict, specifically, a period in which the rise of patrilineal clan-based societies led to warfare in which entire male lineages were eliminated while women were absorbed into victorious groups. The rise of the first complex societies, with their hierarchies and their competition for resources and their organization of violence, may have been catastrophic for men in ways that left a permanent mark on the human genome. The events that caused this bottleneck occurred within the span of recorded history, in the same centuries that saw the rise of the first cities, the first written laws, the first armies. The world that produced civilization also, apparently, produced a period of violence so sustained and so systematically directed at particular male lineages that it reshaped the genetic inheritance of the entire species. The human lifespan is, by primate standards, extraordinarily long, and the post-reproductive period of life, particularly in women, is one of the most puzzling features of human biology from an evolutionary perspective. Most animals in the wild die before or shortly after they lose the ability to reproduce. From a strict Darwinian standpoint, a post-reproductive individual contributes nothing to the propagation of its genes and should not, therefore, be the subject of evolutionary investment. The fact that human women routinely live decades past menopause in conditions of reasonable health, with continued cognitive and physical capacity, requires explanation. The most widely accepted explanation is the grandmother hypothesis, proposed by the anthropologist Kristen Hawkes. The argument is that post-reproductive women who invest in the survival of their grandchildren, providing food, childcare, accumulated knowledge, and social support, significantly increase the survival and reproductive success of those grandchildren. Because grandchildren share 1/4 of their grandmother's genes, this investment has real genetic payoff. The implication is that the long human lifespan, and specifically the survival of women well past reproductive age, was shaped by the adaptive value of grandmothering. The wisdom of age, the accumulated knowledge of a long life, the capacity to help raise the next generation, these were not incidental features of human longevity. They were its cause. Evolution built the long human life because grandmothers were useful. The human capacity for what psychologists call theory of mind, the ability to understand that other beings have mental states different from one's own, is one of the most distinctive and consequential features of human cognition. Theory of mind allows a human being to model the beliefs, desires, intentions, and knowledge of others, to ask not just what is happening, but what another person thinks is happening, what they want, what they know and don't know, and how their behavior can be predicted or influenced based on those internal states. This capacity develops in human children at around age 4, and its presence or absence has profound consequences for social functioning. It is the cognitive foundation of empathy, of deception, of teaching, of storytelling, of law, of politics, and of virtually every complex social interaction. Great apes show some precursors to theory of mind but do not demonstrate the full capacity reliably. The gap between human and ape social cognition, in the sophistication with which mental states are modeled and manipulated, is one of the clearest cognitive distinctions between our species and our closest relatives. Theory of mind is the reason that humans can cooperate at scales that no other species approaches. The ability to model another mind is the foundation of everything that makes human social life distinctively human. The human skeleton contains clear evidence of its evolutionary history, structural compromises and imperfections that make perfect sense as the residue of an ancestor that walked on 4 limbs. The human spine, which evolved from the horizontal spine of a quadruped into the vertical spine of a biped, is subject to problems, herniated discs, lower back pain, sciatica, that are, in a meaningful sense, the cost of upright walking. The lumbar curve that allows humans to stand erect also concentrates stress on specific vertebrae in ways that cause pain for a significant proportion of the population across their lifetime. The human birth canal, which narrowed as the pelvis adapted to bipedal locomotion, creates a tension with the expanding human brain that makes human childbirth the most dangerous of any primate species. The head of a human infant is at the extreme limit of what the birth canal can accommodate. Human newborns are uniquely helpless and underdeveloped compared to the newborns of other great apes, born, effectively, a year too early, because staying in the womb any longer would make birth impossible. The human knee must bear the full weight of the body on a single joint during walking, in a way no 4-legged animal requires. It is similarly prone to injury and degeneration over a lifetime of use. The body is not designed. It is accumulated. And the accumulation shows its history in every joint and curve and compromise. Skin color in humans is one of the most recent and rapidly evolved traits in our species, and its variation reflects adaptation to ultraviolet radiation, not any deeper biological division. Modern humans who left Africa and moved into higher latitudes encountered a different relationship with sunlight than their ancestors in equatorial Africa had experienced. At high latitudes, the lower angle of the sun means less UV radiation reaches the skin. Dark skin, which is highly effective at blocking UV radiation and preventing the folate degradation associated with intense sun exposure, became less adaptive in low UV environments. In low UV environments, the production of vitamin D, which requires UV radiation to synthesize in the skin, became a more pressing selective pressure. Lighter skin, which allows more UV penetration, is more efficient at vitamin D synthesis in low-light conditions. Over tens of thousands of years, populations at higher latitudes evolved lighter skin as an adaptation. The genetic evidence shows that this process happened multiple times independently. Europeans and East Asians are not light-skinned for the same genetic reasons. Their skin lightened independently, through different mutations, in response to the same environmental pressure. Skin color is, in evolutionary terms, a recent and superficial adaptation, the body's local solution to the problem of how much sunlight is available. It has been made to carry a weight of meaning in human social history that has no biological basis whatsoever. The first cities, the largest and most complex human settlements ever built up to that point, appeared in Mesopotamia, in the river valleys of the Tigris and Euphrates, approximately 5,000 to 6,000 years ago. Uruk, in what is now southern Iraq, is the earliest known city by most definitions, a settlement that by 3000 BCE may have housed as many as 50,000 to 80,000 people, surrounded by an agricultural hinterland that fed the urban population, organized around a monumental temple complex at its center. The city required, and in turn produced, a series of inventions that changed the nature of human society permanently. Writing cuneiform script pressed into clay tablets appears to have been invented primarily as an accounting technology, to keep track of the grain stores and livestock and labor obligations of a population too large for individual memory to manage. The first written records are not poetry or history or law. They are receipts. Lists. The bureaucratic infrastructure of a complex economy. The city also produced, for the first time, the division of labor at scale: potters, weavers, metalworkers, scribes, priests, soldiers, merchants, people who spent their entire lives doing a single specialized thing, dependent on the labor of everyone else for everything they did not produce themselves. The city was made possible and necessary by the agricultural surplus that could feed people who did not farm, freeing them to do everything else that civilization would eventually become. Writing, the technology of recording language in a physical medium, was invented independently at least 3 times in human history, and possibly more. The Sumerian cuneiform of Mesopotamia, the Chinese script of the Shang dynasty, and the Mesoamerican writing systems of the Maya and their predecessors all appear to have developed independently, with no contact between the cultures that created them. Each responded to similar pressures: the need to manage complex economies, to transmit information across time and distance, to preserve what memory alone could not hold. The earliest Sumerian writing, dating to around 3200 BCE, consists almost entirely of administrative records, inventories of grain, lists of workers, records of transactions. Writing began as bookkeeping. The step from accounting to literature, from recording quantities to recording thoughts, took centuries. Before writing, all human knowledge was oral. Everything that a civilization knew, its history, its laws, its stories, its technical knowledge, existed only in human memory and human speech. When the people who held that knowledge died, the knowledge was at risk of dying with them. Writing changed this. It externalized memory. It made knowledge independent of any individual mind, capable of surviving the deaths of everyone who had originally possessed it. The words on a clay tablet pressed by a Sumerian scribe's hands 5,000 years ago are still readable today. The knowledge survived. The scribe did not. The agricultural revolution did not merely change how humans ate. It changed human bodies in ways that are still visible in the archaeological record and still felt in living bodies today. Before agriculture, the human diet was highly varied, dozens of different plant foods, a range of animals, seasonal variation that prevented any single nutritional deficiency from becoming chronic. The agricultural diet concentrated calories in a small number of staple crops, wheat, rice, maize, that were highly productive but nutritionally incomplete. The first farmers ate more calories than their hunter-gatherer predecessors but got less of almost everything else: less protein, less fat, fewer vitamins, fewer minerals. The bones of early agricultural populations reflect this. They are shorter than those of contemporary hunter-gatherers in the same region. Their teeth show higher rates of decay and disease, caused by the carbohydrate-rich diet. Their skeletons show signs of nutritional deficiencies: iron deficiency, anemia, vitamin D deficiency, that are rare in hunter-gatherer remains. The average height of human populations in the regions where agriculture first appeared declined by several inches in the first few thousand years after its adoption, and did not return to pre-agricultural levels until the 20th century. We are only now, with the diversity of modern food systems and the understanding of nutrition that the last century has produced, recovering the dietary breadth that our hunter-gatherer ancestors had as a matter of course. The emergence of Homo sapiens was accompanied by a dramatic increase in the complexity of material culture, the range and sophistication of tools, ornaments, and symbolic objects produced. The period from roughly 50,000 to 40,000 years ago is sometimes called the Upper Paleolithic Revolution or the Great Leap Forward, a term referring to a sudden apparent explosion of behavioral modernity visible in the archaeological record across Europe and parts of Africa and Asia. Within a relatively short time, the record shows composite tools with multiple components, long-distance trade in specific raw materials, personal ornaments made from shells and teeth, musical instruments, and the first unambiguous figurative art. Some researchers believe this represents a genuine cognitive revolution, a change in brain organization or function that produced qualitatively new capabilities. Others argue that the change is partly an artifact of where archaeologists have been looking, and that evidence of comparable behavioral complexity in Africa predates the European record by tens of thousands of years. What both sides agree on is the endpoint. By 40,000 years ago, the humans of the Upper Paleolithic were producing a material culture recognizably continuous with our own. They were making things to be beautiful, not merely functional. They were trading objects over hundreds of kilometers. They were burying their dead with care and objects. They were, in all the ways the archaeological record can reveal, fully human. The human capacity for cumulative culture, the ability to build on the knowledge and inventions of previous generations, each generation starting where the last left off rather than beginning again from the beginning, is one of the most consequential differences between humans and every other species. Individual animals can learn. Many species can transmit learned behaviors from one individual to another. But the accumulation of knowledge across generations, the ratchet effect by which each generation inherits the full sum of what all previous generations discovered, is a distinctively human capability. A chimpanzee cannot build on what the previous generation of chimpanzees invented. Each generation of chimpanzees discovers, on its own, the same techniques for cracking nuts or fishing for termites that previous generations discovered. The knowledge is transmitted imperfectly and incompletely, and it does not accumulate. There is no chimpanzee equivalent of the internet, of medicine, of the accumulated scientific knowledge of the last 400 years, not because chimpanzees lack intelligence, but because they lack the cultural infrastructure for cumulative transmission. This infrastructure, language, writing, institutions, education, is what makes human history different from the history of any other species. The human alive today is not smarter than the human alive 50,000 years ago. The brain has not changed. What has changed is the accumulated knowledge that brain is born into the millennia of discoveries and inventions and ideas that every human inherits without effort, simply by being born into a human world. The Neolithic Revolution, the transition from nomadic hunter-gatherer life to settled agricultural communities, happened at different times in different parts of the world, and in some places, it has not fully happened yet. the last fully nomadic hunter-gatherer societies on Earth, populations that have maintained the way of life that characterized all of humanity for most of its history, have been studied extensively by anthropologists, and what those studies have revealed is consistently surprising to people accustomed to thinking of hunter-gatherer life as difficult and precarious. The Yikung San people of the Kalahari, studied in detail by the anthropologist Richard Lee in the 1960s, were found to spend an average of 15 to 20 hours per week on subsistence activities, gathering food and water, hunting. The rest of their time was spent in rest, social activity, storytelling, and play. They were well-nourished, had detailed knowledge of their environment, and lived in egalitarian social groups without permanent hierarchy. The anthropologist Marshall Sullins coined the term the original affluent society to describe this pattern, suggesting that hunter-gatherers achieved a kind of material sufficiency not by producing a great deal but by wanting very little. Their needs were modest. Their environment, managed through generations of detailed knowledge, met those needs. The poverty of hunter-gatherer life, seen from the outside, looks very different from the inside. The human immune system carries within it a record of every pathogen that has shaped our evolution, a molecular memory of ancient encounters between our ancestors and the diseases that tried to kill them. The major histocompatibility complex MHC, the system of proteins that allows immune cells to recognize foreign invaders, is the most genetically diverse region in the human genome. The extraordinary diversity of MHC variants in living human populations reflects millions of years of arms race evolution between human immune systems and the pathogens trying to evade them. Each variant that survives in the population is there because it helped some ancestor survive some disease that killed others. When two people feel a strong and inexplicable physical attraction, research suggests that MHC compatibility plays a measurable role. People tend to be attracted to individuals with different MHC types from their own, detected through subtle olfactory cues, the smell of another person. The offspring of parents with different MHC types have more diverse immune systems, better equipped to handle a wider range of pathogens. The biological roots of human attraction are, in part, an immune system calculation. The body, evaluating a potential mate, is asking, would our children be better equipped to survive disease? The feeling that we experience as chemistry or mystery is, at the molecular level, a conversation between two immune systems, comparing notes on what they have survived. The first known burial of a modern human, a deliberate, intentional interment of the dead with goods and pigment, dates to approximately 100,000 years ago, at a site called Kafsa Cave in what is now Israel. The individual buried there was an adolescent, placed in a grave with the skull and antlers of a fallow deer, objects that served no practical purpose in burial but that were clearly placed there with deliberate intention. Ochre pigment was found on and around the bones. What burial means, what it tells us about the mental life of the people who practiced it, is a question that archaeologists and philosophers have debated extensively. At minimum, burial suggests a recognition that the dead person was something more than a body to be left behind, that the relationship between the living and the dead extended beyond the moment of death, that something needed to be done, some acknowledgement made, some care taken. At more than minimum, burial suggests the capacity to think about death abstractly, to understand that death is a category, not just an event, that the self that was present is now absent, that this absence has a meaning that the living need to address. It suggests, in short, the kind of self-awareness and mortality consciousness that may be unique to humans. The adolescent at Kafsa was buried 100,000 years ago by people who understood what death was. We know this because they could not simply leave. The human capacity for music, for perceiving and producing organized sound in ways that move the body and the emotions, appears to be deeply embedded in human biology, not culturally acquired. Infants respond to rhythm and melody before they can speak. Across all cultures ever studied, music is present, no culture has been found without it. The neural substrates for music processing are present and active in human brains regardless of musical training. Certain musical responses, the goosebumps produced by an unexpected harmony, the impulse to move to a rhythm occur in the same brain circuits regardless of cultural background. The evolutionary origin of this capacity is debated. Charles Darwin himself suggested that music might have preceded language in human evolution, that the ancestors of modern humans developed musical vocalizations for social bonding and mate attraction before they developed the combinatorial grammar that makes language what it is. More recent research has suggested that music and language share deep cognitive roots, that the capacity to track and predict sequential patterns in sound essential to both music and language may have developed in the service of both simultaneously. What is clear is that music is not a cultural luxury. It is a biological endowment. The human brain is built for it. Every child born into the world arrives already equipped to receive it, already prepared, before the first note is heard, for the experience of music. The mitochondrial Eve, the woman from whom all living humans inherit their mitochondrial DNA, lived in Africa approximately 150,000 to 200,000 years ago. She was not the only woman alive at the time. She was not, in any meaningful sense, the first woman or the only ancestor of all living humans. She is simply the most recent common ancestor in the maternal line, the woman whose unbroken line of daughters has continued without interruption to the present day, while all other female lines from her period have died out. The concept is sometimes misunderstood as implying that she was alone, or that she was special in some way that her contemporaries were not. She was not. She was one woman among many, living in a community, probably unremarkable by the standards of her time. The reason her line continued when others did not is largely a matter of chance, the random survival and reproduction of daughters across 150,000 years of human history. Similarly, there is a Y-chromosomal Adam, the most recent common ancestor in the paternal line, the man from whom all living men inherit their Y chromosome. He lived, according to current estimates, between 200,000 and 340,000 years ago, older than mitochondrial Eve, and not her contemporary. Mitochondrial Eve and Y-chromosomal Adam never met. They could not have. They are the endpoints of statistical genealogical calculations, not a first couple. But they are real people, real ancestors, who lived and breathed and had no idea what they were, in relation to all of us. The discovery of fire, or more precisely, the controlled use of fire, may have done more to change the trajectory of human evolution than any other single development. Before controlled fire, the human day ended with the light. Darkness meant danger, predators, cold, the vulnerability of sleep in an unprotected place. Fire changed the temporal structure of human life. It extended the day into the night, creating hours of warmth and light and relative safety that had not previously existed. The anthropologist Polly Wiesner has studied the content of conversations among the Kung San people at different times of day, and found a striking pattern. Daytime conversations are dominated by practical matters, food, tools, resource management, conflicts. Nighttime conversations, gathered around fire, shift dramatically toward storytelling, singing, the discussion of distant people and distant places, the transmission of cultural knowledge and moral frameworks. Wiesner argues that firelight evenings were the context in which much of the distinctively human cognitive and cultural elaboration of the Upper Paleolithic developed, that the protected, extended evening around a fire was the first classroom, the first theater, the first space set aside for the transmission of culture rather than the execution of survival. Fire gave humanity the night. And in the night, humans told each other stories. And the stories became civilization. The human sense of smell, often described as the weakest of the human senses, far inferior to that of dogs or bears, is, in absolute terms, far more powerful than is commonly believed. A human nose contains roughly 400 types of olfactory receptors, capable of detecting and distinguishing an estimated 1 trillion different odors. Recent research has found that trained human smell specialists, perfumers, sommeliers, researchers, can detect and identify odors at concentrations previously thought to be below the threshold of human detection. What humans genuinely lack, compared to other mammals, is the neural real estate devoted to processing smell. The olfactory bulb, the brain structure that processes scent information, is proportionally much smaller in humans than in most other mammals, reflecting the relative de-emphasis of smell as humans shifted toward greater reliance on vision. But the olfactory system retains a directness of connection to the emotional and memory centers of the brain that no other sense possesses. Visual information and auditory information travel through relay stations before reaching the limbic system. Olfactory information goes there almost directly, which is why a smell can trigger a memory with an immediacy and emotional intensity that no other sensory experience can quite match. The smell of something from childhood can return a person to a specific moment with a vividness that vision and sound rarely achieve. The oldest sensory pathway in the brain remembers what the mind has forgotten. The nose carries the past in a way no other organ does. The human brain undergoes a prolonged period of development after birth, more prolonged, relative to body size and lifespan, than any other known species. A human newborn is, by the standards of other primates, astonishingly helpless. A newborn chimpanzee can cling to its mother immediately after birth. A newborn horse can walk within hours. A human infant cannot hold its own head up, cannot coordinate its movements, cannot do anything that requires the engagement of the higher brain regions. Those regions are not yet functional. The prefrontal cortex, the region associated with planning, impulse control, moral reasoning, and complex social cognition, does not reach full maturity in humans until the mid-20s. No other known species has a development period this long relative to its total lifespan. This extended development is the price of the large brain. The human skull cannot accommodate a fully developed brain at birth. The head that would result would make birth impossible. The brain must do much of its development outside the womb in the first years of life. This creates a period of prolonged dependency unlike anything in the animal world, an extended childhood during which the human being is entirely dependent on care from others. This dependency is also an opportunity. The prolonged development of the human brain is the period during which culture is installed, during which language, values, emotional regulation, social skills, and all the other non-genetic inheritances that make a human being human are laid down in the developing neural architecture. The long childhood is not a weakness. It is the mechanism by which humanity reproduces itself. The last ice age, the period of maximum glacial advance that peaked approximately 20,000 years ago, shaped the distribution of human populations across the globe in ways that are still visible in the genetic and linguistic diversity of living people. At the glacial maximum, massive ice sheets covered much of North America and Northern Europe. Sea levels were lower by as much as 120 meters, exposing land bridges between landmasses currently separated by water. The landmass known as Beringia, the connection between Siberia and Alaska, was exposed, allowing the movement of animals and eventually people between the Old World and the New. Human populations in the northern latitudes contracted into refugia areas where the climate remained livable despite the general cold, and were isolated from each other for thousands of years. When the ice retreated, these populations expanded outward from their refugia, recolonizing the lands that had been abandoned. The genetic signatures of these expansions, the founder effects produced when small isolated populations repopulate large areas, are still visible in the genomes of living Europeans, East Asians, and the indigenous peoples of the Americas. The Ice Age is not ancient history in the sense of being irrelevant to the present. The genetic structure of living human populations, the distribution of language families across continents, the locations of the earliest post-glacial settlements, all of these are shaped by the retreat of ice that began roughly 15,000 years ago. The Americas were the last habitable continents to be reached by modern humans, and the timing and route of that arrival has been one of the most debated questions in American archaeology for over a century. The long-dominant model held that the first Americans crossed the Bering Land Bridge from Siberia approximately 13,000 years ago, moving southward through an ice-free corridor that opened between the retreating Laurentide and Cordilleran ice sheets. This model was based on the archaeological record, which showed abundant evidence of human presence across North and South America from approximately 13,000 years ago. That model has been significantly revised by discoveries at sites that predate it. Monte Verde in Chile, with a secure date of approximately 14,500 years ago, shows human occupation at the tip of South America before the ice-free corridor was open. This requires either an earlier crossing via Beringia, or, increasingly favored by researchers, a coastal migration, people moving southward along the Pacific coast in small watercraft, stopping at ice-free refugia along the way. By the time Europeans arrived in the 15th century CE, the Americas were home to populations in the tens of millions, speaking hundreds of distinct languages, organized in societies ranging from small nomadic bands to the vast empires of the Aztec and Inca. All of this, every civilization, every language, every tradition, descended from the small founding population that crossed the threshold from the old world into the new, somewhere between 15,000 and 20,000 years ago. The human capacity for cooperation with strangers, for working alongside people to whom we have no genetic relationship and whom we have never met before is, in evolutionary terms, deeply unusual. Most animal cooperation is explained by kin selection cooperation with genetic relatives, whose survival increases the propagation of shared genes, or by reciprocal altruism cooperation with individuals you expect to encounter again, where both parties benefit over time from mutual assistance. Human cooperation extends far beyond both of these. Humans cooperate with strangers in one-time interactions where there is no expectation of future reciprocity and no genetic relationship. They do so at scales that encompass millions of individuals in economic markets, in armies, in political systems, in the global supply chains that produce the objects surrounding any person living in a modern economy. The mechanism that makes large-scale cooperation with strangers possible is, according to the most widely accepted current account, the shared belief in institutions, norms, and symbols that have no physical existence but that nonetheless organize behavior. Money works because everyone agrees it works. Laws bind because enough people agree to enforce them. Nations exist because enough people believe in them. The political philosopher calls these shared fictions. The evolutionary anthropologist calls them the cognitive foundation of human sociality. Either way, they are the mechanism by which a primate whose ancestors lived in groups of 150 now organizes itself across populations of billions. The human preference for cooked food is so deeply embedded that it manifests as a physical craving, a sensory response to the smell and appearance of cooked meat and cooked carbohydrates that has no direct analog in our closest primate relatives. The Maillard reaction, the chemical process that produces the browning and aroma of cooked meat, bread crust, roasted coffee, and countless other cooked foods, occurs at temperatures above approximately 140 degrees Celsius. It produces hundreds of different flavor compounds simultaneously, creating the complex aromas that humans find intensely appealing. Chimpanzees and other great apes show no particular preference for cooked food over raw. Humans do strongly and consistently. Research by Richard Wrangham and his colleagues has found that humans not only prefer cooked food but are specifically calibrated to it in ways that raw food diets cannot fully satisfy. People who attempt to subsist entirely on raw food diets typically lose significant body weight, and many women on such diets cease menstruating, a sign of insufficient caloric intake despite eating large quantities of food. The human digestive system, shaped by millions of years of cooked food consumption, is optimized for food that has already been partially broken down by heat. It extracts more energy from cooked food than from the same food eaten raw. The preference for the smell of cooking, that fundamental human response to warmth and the transformation of raw things into something else, is the body recognizing its own requirements. We evolved to need the fire. The appetite came with the body. Laughter, the involuntary vocalization produced by humor, play, and social bonding, is one of the oldest and most distinctively human behaviors, with roots in our primate ancestry. Chimpanzees and other great apes produce a panting vocalization during play, sometimes described as a breathy, open-mouthed sound that is believed to be homologous with human laughter. It occurs in the same contexts: tickling, play fighting, social games. It appears to serve the same function, signaling that the interaction is playful, not aggressive, that apparent conflict is not to be taken literally. Human laughter differs from ape laughter in important ways. It is more varied in its acoustic form. It can be produced voluntarily, though genuine laughter is involuntary. It can be faked. Humans laugh socially, to signal affiliation, in contexts that do not involve genuine amusement. And it is significantly more contagious. The sound of human laughter triggers laughter in listeners more reliably and more powerfully than chimpanzee panting triggers laughter in other chimpanzees. The neuroscientist Robert Provini has found that laughter is predominantly a social behavior, that humans are 30 times more likely to laugh in the presence of others than alone. The function of laughter, in this analysis, is less about humor and more about social bonding, a signal of safety, of shared understanding, of membership in a group where conflict is not expected. Laughter is the sound of trust. It is one of the oldest sounds the human face makes. And it is still doing, 35 million years after its ancestor first breathed it in play, exactly what it was designed to do. The relationship between the human brain and sleep is one of the most active areas in current neuroscience, and what research is revealing is that sleep is not simply rest. It is an active biological process essential to virtually every cognitive and physical function. During sleep, the glymphatic system, a waste clearance system in the brain that functions primarily during sleep, flushes out metabolic byproducts including the amyloid proteins associated with Alzheimer's disease. Memory consolidation occurs during sleep, as the hippocampus replays the day's experiences and transfers them to long-term storage in the cortex. Emotional processing occurs during REM sleep, reducing the emotional intensity of distressing experiences. Humans sleep differently from most other mammals in a way that may reflect the transition to ground sleeping with fire. Most primates sleep in trees, where safety requires light, fragmented sleep with frequent waking. Humans, sleeping in protected groups near fire, could afford the deeper, more consolidated sleep that REM-rich human sleep represents. The result is that humans get less total sleep than most primates, roughly 8 hours compared to the 10 to 15 hours typical of other great apes, but more of that sleep is the deep, cognitively productive kind. Human sleep, shaped by fire and group protection, is qualitatively different from the sleep of our closest relatives. Sleep is not the absence of being human. It is one of the things being human requires. The development of writing did not simply record human thought. It changed the nature of human thought. The psychologist and philosopher Walter Ong spent much of his career studying the difference between oral cultures, cultures in which all knowledge is transmitted through speech, and literate cultures, cultures in which writing is available. His central argument was that literacy does not merely add a technology to an existing cognitive system. It restructures the cognitive system itself. Oral cultures, Ong argued, think in specific ways, preferring concrete images over abstract categories, situational knowledge over analytical frameworks, narrative over logic. These are not deficiencies, they are adaptations to a world where knowledge must be kept alive in memory, where the memorable and the vivid are functionally necessary. Abstract categories are harder to remember than stories. Writing changes this by externalizing memory. When knowledge can be stored outside the mind is freed from the obligation to remember and can devote itself to analysis. Writing makes possible the linear argument, the systematic classification, the abstract definition, modes of thought that are essentially impossible to sustain without the ability to go back and reread, to see the structure of an argument laid out spatially on a page. The way educated people in literate societies think, the categories they use, the analytical habits they apply, the distinction they draw between feeling and reasoning is not natural. It is a consequence of writing, installed through years of education, available only to those with access to literacy. Most of human thought, for most of human history, did not work this way. The transition from hunter-gatherer life to agricultural life produced, for the first time in human history, the conditions necessary for epidemic infectious disease. Dense, sedentary populations living in close contact with domesticated animals are ideal environments for the transmission of pathogens. Many of the most significant infectious diseases in human history, smallpox, measles, influenza, tuberculosis, crossed from animal reservoirs into human populations in the context of agricultural life and then spread explosively through the dense settled communities that agriculture had made possible. The consequences were catastrophic for populations that had not previously been exposed to these diseases and therefore had no immune memory of them. When Europeans arrived in the Americas in the late 15th century, they brought with them the pathogens of 10,000 years of agricultural diseases against which European populations had developed partial immunity through millennia of exposure, but which were entirely new to the indigenous peoples of the New World. Current estimates suggest that between 50 and 90% of the indigenous population of the Americas died in the century following European contact, the largest demographic catastrophe in human history, caused not primarily by conquest or violence but by disease. The civilizations that Europeans encountered, and subsequently described as primitive or sparse, were in many cases the remnants of societies that had recently lost the majority of their population. The biological history of humanity is, in part, a history of pathogens. The diseases that shaped our evolution, our immune systems, and our history are as much a part of the human story as anything we made or built or believed. The human face is the most expressive in the animal kingdom, not because humans feel more, but because humans need to communicate what they feel with a precision and range that no other species requires. The human face contains more than 40 distinct muscles, many of which exist solely to produce facial expressions. They have no other mechanical function. The corresponding muscle count in other primates is lower, and the dedicated expression muscles fewer. Human facial muscles can produce a range of expressions that researchers have documented in the hundreds, many of them universally recognized across cultures with no prior contact. The psychologist Paul Ekman spent decades studying facial expressions across cultures and identified a set of basic emotional expressions: happiness, sadness, fear, anger, disgust, surprise, and contempt that appear to be universal, recognized consistently by people in every culture he studied, including cultures that had had no contact with Western media. The evolutionary explanation for the expressiveness of the human face lies in the social complexity of human life. In a species that cooperates at the scale humans do, that forms alliances and detects betrayal and reads intention in the behavior of others, the ability to communicate emotional state quickly, precisely, and involuntarily is enormously valuable. The face is a broadcasting system, transmitting information about internal states, about intentions, about the reliability of promises, that evolved in the context of the social demands that only humans face. The face you show the world is the product of millions of years of social evolution. Every expression you make involuntarily is ancient. The surprise, the contempt, the grief, they were on faces that looked into a very different world, and they meant, then as now, exactly what they mean. The Homo naledi, a hominin species discovered in a cave system in South Africa in 2013, presents one of the most puzzling mysteries in the study of human origins. Homo naledi had a brain roughly the size of an orange, far smaller than modern humans and not significantly larger than earlier hominins. Its hands and feet were well adapted for both tool use and climbing. It survived, in some form, until somewhere between 236,000 and 335,000 years ago, meaning it was alive at the same time as early Homo sapiens. What makes Homo naledi so puzzling is where the fossils were found. The bones of at least 15 individuals were discovered deep in a cave system, in a chamber accessible only through a narrow vertical chute that required considerable effort to negotiate. There is no evidence that any other large animals entered the chamber. There is no evidence of water flow that could have carried the bones there. The bones appear to have been deliberately placed. If the bones were deposited deliberately, if Homo naledi, with its small brain and its primate-like body, was taking its dead to a specific, difficult to reach underground location, then deliberate disposal of the dead may not be a uniquely modern human behavior, and the cognitive complexity required for it may be far less than was previously assumed. Homonality has not been fully explained. It sits in the record as a question, a small-brained, ancient-looking species, surviving into the age of modern humans, apparently doing something with its dead that we do not yet understand. The human capacity for religious and spiritual belief, for positing the existence of forces, beings, or realities beyond the perceptible world, appears to be a cognitive byproduct of other features of the human mind rather than a behavior directly selected for. The cognitive scientist Pascal Boyer has argued that religious concepts are particularly memorable in the human mind because they violate our intuitive expectations about the world in specific ways, they combine ordinary properties with counterintuitive ones, and that this memorability makes them easy to transmit and difficult to forget. A God who is everywhere at once, who knows all thoughts, who cannot die. These violations of our intuitive understanding of persons and bodies are precisely the kind of information that sticks in human memory. The agency detection system, the hair-trigger tendency of the human brain to infer the presence of an intentional agent behind events, even when none is present, is another cognitive feature that researchers believe contributes to religious belief. A brain that errs on the side of detecting agency, that hears a noise in the forest and assumes something with intentions made it, will survive more predator encounters than a brain that requires strong evidence before inferring agency. The cost of this hair trigger is a mind that sees intention everywhere, in storms, in illness, in the movements of the stars. A mind that is very well designed for detecting predators and social agents is also, by the same design, prone to finding agents where none exist. Whether that is the full story of religious belief is a question that neuroscience, philosophy, and theology have not finished asking. The human gut microbiome, the community of trillions of microorganisms living in the human digestive tract, is so tightly integrated with human physiology that some researchers have begun to describe it as an organ. The gut microbiome influences immune function, metabolism, and increasingly, research suggests, mental health and behavior. The gut and the brain are connected through the vagus nerve and through the production of neurotransmitters, including serotonin, approximately 90% of which is produced not in the brain but in the gut, in ways that are only beginning to be understood. The composition of the human gut microbiome has changed dramatically since the adoption of agriculture and even more dramatically since the industrialization of the food supply. Hunter-gatherer populations studied by microbiologists have microbiomes of significantly greater diversity than those of people living in industrial societies, a diversity that appears to be associated with immune function and metabolic health. The species of gut bacteria present in living humans include some that appear to have co-evolved with the human lineage over millions of years, ancient companions, maintained through the generations because they contributed something to the survival of the organisms that harbored them. They are not human, genetically. But they are part of what a human being is, functionally. They have been inside us longer than we have known they existed. The colonization of the Pacific, the final great chapter of human geographic expansion, in which humans reached the islands of Polynesia including Hawaii, Easter Island, and New Zealand, was accomplished by seafarers navigating open ocean without instruments, using knowledge systems that modern navigation science has only recently begun to fully appreciate. Polynesian navigators used the stars, the patterns of ocean swells, the behavior of birds, the color of the water, and the feel of the wind to cross thousands of kilometers of open Pacific with accuracy that modern sailors using GPS have found genuinely difficult to replicate. The knowledge was transmitted orally, from master navigator to student, through years of apprenticeship and practice. It was not written down. It was embodied, carried in the body of the navigator, in the sensitivity of the skin to wave patterns, in the memory of star positions across thousands of hours of observation. New Zealand was reached by Polynesian voyagers approximately 700 years ago, the last large landmass on Earth to be settled by humans. The settlement of New Zealand marks the completion of the human occupation of the habitable world that began when the first hominins walked out of the African forest several million years ago. The species that started in one African landscape eventually reached every island, every continent, every inhabitable environment on the planet. The journey took approximately 6 million years, involved dozens of species and hundreds of thousands of generations, and ended, on a small island in the South Pacific, with a canoe landing on a beach. The development of money, a standardized medium of exchange, was one of the most consequential cognitive and social inventions in human history, because it made possible trade between strangers who had no prior relationship and no expectation of future contact. Before money, exchange between strangers required a coincidence of wants. You had something I needed, and I had something you needed, and we happened to find each other. The limits this placed on trade were severe. It restricted exchange to small, local networks where relationships were personal and continuous. Money replaced relationship with symbol. A coin or a token accepted by everyone in a system of exchange is accepted not because the holder trusts the specific person offering it, but because they trust the system, the institution that guarantees its value. For the first time, strangers could exchange goods without prior relationship, without expectation of future contact, without any personal knowledge of each other at all. The cognitive leap required to understand money, to treat an object with no intrinsic value as a store of value, to trust a symbol rather than a person, is a specific manifestation of the human capacity for shared fictions. The coin is valuable because we agree it is valuable. The agreement is what makes it real. This capacity to organize behavior around shared symbols and agreed upon fictions is one of the most powerful forces in human history. Money, law, nations, corporations, all of them are, in this sense, the same kind of thing. Agreements that work because enough people believe in them. The concept of childhood, of a distinct, protected phase of human life set apart from adult responsibilities, deserving of specific care and specific experiences, is, in its modern form, a relatively recent cultural construction. For most of human history, children were understood as small adults, not as a categorically different kind of person requiring a categorically different kind of treatment. In medieval Europe, children as young as 7 were expected to participate fully in the work of the household. There was no separate literature for children, no separate spaces designed for children, no legal concept of childhood as a protected status. The historian Philippe Aries argued in 1960 that the modern concept of childhood was invented in early modern Europe, as economic development, reduced child mortality, and changing family structures made it possible and desirable to invest more in fewer children rather than less in more. As children became less likely to die before adulthood, they became more emotionally significant, and the relationship between parents and children became more emotionally intense. What was not invented is the biological reality of the prolonged human developmental period, the fact that the human brain takes 25 years to fully mature, that the human child requires sustained care and education for a decade and more. The cultural concept of childhood was constructed. The biological basis for it was always there, waiting to be recognized. The human propensity for storytelling, for organizing experience into narrative form, with characters and causation and resolution, appears to be one of the most fundamental features of the human mind. The cognitive scientist Jerome Bruner distinguished between two modes of human thought: the logico-scientific mode, which seeks general truths through abstraction and formal reasoning, and the narrative mode, which seeks human truth through stories, characters, and the particularity of specific events. Both are distinctively human. But the narrative mode is, by most accounts, more ancient, more universal, and more deeply embedded in human cognition. Across all cultures, humans tell stories. The structural features of stories: a protagonist with desires and obstacles, a sequence of events with causation, a resolution, appear to be universal. The specific stories differ. The form is the same. This universality suggests that narrative is not a cultural technology, like writing or mathematics, but something more fundamental, a default mode of the human mind, the shape into which human experience naturally falls. Recent neuroscience has found that narrative processing engages more brain regions simultaneously than almost any other cognitive task, activating sensory cortices, motor cortices, emotional processing regions, and social cognition networks in an integrated way that pure logical reasoning does not. A story, heard or read or watched, literally simulates the experiences it describes, running a neural model of the events in the listener's brain. This is why stories teach. The simulation they run in the listener is, neurologically, a kind of experience. The lesson learned from a story is learned in the same neural circuits as the lesson learned from life. The human eye is capable of detecting a single photon of light under ideal conditions, a sensitivity so extreme that it approaches the theoretical physical limit of light detection. More remarkably, the human eye can adapt to an extraordinary range of light conditions, from the full brightness of midday sun to the dim light of a quarter moon, a range of roughly 1 trillion to 1. No artificial sensor approaches this dynamic range. The adaptation happens through multiple mechanisms operating simultaneously. The pupils dilate and contract, the photoreceptors in the retina shift between types suited to bright and dim light, and the neural processing of the visual signal adjusts to extract the maximum information available. The human visual system is so powerful because vision was the primary sense through which early primates navigated their world. The ancestral primates that gave rise to the human lineage were tree dwellers who depended on precise depth perception for moving through the branches, and on color vision for identifying ripe fruit. These pressures selected for the forward-facing eyes, overlapping visual fields, and trichromatic color vision that characterize all great apes and humans. What we look at, and how we look, the way human eyes move across a face, reading expression, the way they follow motion, the way they search for the unexpected in a familiar scene, reflects the visual demands of a social primate living in a visually complex world. The eye evolved in the forest. It came with us to every other environment we subsequently occupied. The transition to bipedalism, walking upright on 2 legs, freed the human hands for purposes other than locomotion and is widely considered one of the key enabling adaptations that led to tool use, technology, and the elaboration of human culture. But bipedalism also imposed costs that are still paid by every human being alive. The upright pelvis is less efficient for childbirth than the quadruped pelvis. The upright spine concentrates mechanical stress on the lower back in ways that cause chronic pain for a large fraction of the human population. The upright posture raises the center of gravity, making balance more demanding and falls more consequential. The question of why bipedalism evolved, what selection pressures favored walking upright over the more mechanically efficient four-legged locomotion of our ancestors, has been debated for decades. Current evidence suggests that bipedalism may have evolved in a context of increasing open grassland environments, where upright walking was more thermally efficient than four-legged locomotion, exposing less surface area to the sun and allowing more effective heat dissipation through sweating. Alternatively, it may have evolved in a woodland context, where upright posture allowed early hominins to see above the grass to detect predators and prey, or to carry food and infants while moving between scattered resource patches. What is clear is that bipedalism was not simply the removal of one mode of locomotion and its replacement by another. It was a wholesale reorganization of the body, the spine, the pelvis, the knee, the foot, the skull attachment that changed everything about how the hominin body moved through the world. The emergence of symbolic thought, the capacity to let one thing stand for another, to use a mark or a sound or an object to represent something else, is the cognitive threshold most directly responsible for art, language, religion, and every other distinctively human cultural achievement. Before symbolic thought, the world was only itself. A bone was a bone. A sound was a sound. The cognitive step that allows a sound to mean something other than itself, to function as a word, or that allows a mark on a wall to represent an animal rather than simply being a mark, is the step that separates human cognition from that of every other species. The archaeological evidence for symbolic thought is imprecise and contentious, because the inferential chain from physical object to cognitive capacity is long and uncertain. Shell beads drilled for stringing found in North Africa dating to approximately 130,000 years ago suggest that the people who made them were using objects to represent something: social identity, group membership, status. The object is the symbol. The symbol implies the capacity. What symbolic thought made possible was not just language and art, but the entire structure of human social life, the institutions, the laws, the categories, the shared meanings that organize human behavior at scales impossible without them. Every system by which humans organize themselves, every government, every economy, every religion, is built from symbolic representations. Remove the capacity for symbolism and human civilization dissolves instantly into something much older and much simpler. The single cognitive step, the capacity to let one thing mean another, is the step from animal to human. We do not know exactly when it happened. We know that it changed everything. The human tendency toward in-group favoritism and out-group suspicion, the psychological predisposition to trust and cooperate more readily with people perceived as belonging to the same group, is one of the most studied and most consequential features of human social psychology. Experiments have found that this tendency activates rapidly on minimal evidence. People will form in-group preferences based on trivially arbitrary group assignments, being told they prefer a particular abstract painter over another, for instance, and these preferences affect subsequent behavior in measurable ways. The in-group is favored. The out-group is viewed with greater suspicion. This psychological architecture reflects the social environment in which human beings evolved: small groups competing for resources, where trust within the group was adaptive and suspicion toward outsiders was prudent. It was a sensible set of responses to the world of 50,000 years ago. It is the same set of responses that produces tribalism, xenophobia, nationalism, and intergroup violence in the world of today. The same cognitive machinery that allowed small bands of early humans to survive through internal solidarity is the machinery that drives the human capacity for organized hatred. The software was written for a different world. It runs on the hardware of this one. Understanding this does not resolve the tension, but it locates it accurately, not in some flaw that history introduced into an originally uncorrupted nature, but in the deepest architecture of the social mind, put there by the same processes that put everything else there. The human nose, the structure that sits at the center of the face and whose shape has generated more cultural anxiety than almost any other anatomical feature, evolved its protruding form not primarily for smell but for warming and humidifying inhaled air. In cold, dry climates, air inhaled directly into the lungs without warming or humidification can damage the delicate tissues of the respiratory tract. The nose's elaborate internal architecture, the turbinates, the mucous membranes, the convoluted passages, warms and moistens inhaled air before it reaches the lungs. The protruding external nose increases the length of the air passage and the surface area available for this conditioning. Populations that evolved in cold, dry climates tend to have narrower, longer noses, a shape that maximizes the conditioning pathway. Populations that evolved in warm, humid climates tend to have shorter, broader noses, a shape that is less necessary for conditioning and more permissive of direct airflow. The extraordinary range of nose shapes across human populations, a range that has been given enormous cultural significance throughout human history, is, in biological terms, an adaptation to climate. The architecture varies because the climates vary. The nose that evolution built for the Arctic is different from the nose it built for the tropics, because the problems they need to solve are different. The part of the human face most loaded with social meaning and aesthetic judgment is, in the genome, a piece of environmental engineering. It warms the air. Nothing more and nothing less than that. The domestication of cattle, the transformation of the wild aurochs into the domestic cow, had consequences for human evolution that continue in the bodies of a significant portion of the living human population. The aurochs was a large, aggressive wild bovine that ranged across Eurasia and North Africa. Its domestication, which occurred approximately 10,000 years ago in the Near East, produce not only a source of meat and labor but a source of milk, a nutrient-rich liquid that adult mammals are not, in general, equipped to digest. All mammal infants produce lactase, the enzyme required to digest lactose, the sugar in milk. In most mammal species, lactase production drops sharply after weaning. There is no nutritional advantage to digesting milk in adulthood, so the enzyme is not maintained. For most of human prehistory, most adult humans were lactose intolerant, like most adult mammals. But in populations that kept dairy animals, individuals who happened to carry genetic mutations maintaining lactase production in adulthood had access to a rich, reliable food source that others did not. Over thousands of years, these individuals survived and reproduced more successfully, and the mutation spread through the population. Lactase persistence, the ability to digest milk in adulthood, evolved independently in multiple cattle herding populations across Europe, Africa, and the Middle East. The genes that make roughly a third of living humans able to drink milk without discomfort are the molecular record of a relationship between people and cattle that is 10,000 years old. The dairy aisle in any modern supermarket is the outcome of a coevolution between a mammal and the animal it decided to keep. The human hand, the structure that has made possible every physical technology humans have ever created, is the result of an evolutionary history that began not with manipulation but with locomotion. The hands of our tree-dwelling primate ancestors were shaped by the demands of gripping branches. The long, curved fingers suited to wrapping around a branch are the evolutionary raw material from which the human hand was derived. The transition to upright walking freed the hands from any locomotor role, making them available for carrying, for tool use, for the fine manipulation that no primate had previously needed at the same scale. The precision grip, the ability to hold a small object between the tips of the thumb and forefinger, is the capability most directly associated with human technological development. It requires the specific proportions of the human hand, the short, strong thumb capable of opposing the other fingers across a wide range of positions, the mobile fingers with their sensitive fingertips. The precision grip is what allows the flint knapper to shape a stone tool, the surgeon to suture a wound, the painter to control a brush, the musician to press a string. It is the physical interface between human intention and the material world, the point where what the mind conceives makes contact with what the hand can do. Every object in your immediate environment that was made by a human being passed through a precision grip at some point in its production. The hand is the oldest manufacturing technology. It has been in continuous production for at least 2 million years. The question of whether early Homo sapiens interbred with archaic human populations outside Africa, with Neanderthals, Denisovans, and possibly other unknown groups, was long considered settled in the negative. The prevailing model through most of the 20th century was the complete replacement model. Modern humans left Africa and replaced all archaic populations without interbreeding. The populations were too different. The contact was too brief or too hostile. The evidence for hybridization was considered absent. Ancient DNA analysis overturned this consensus entirely. We now know that modern humans interbred with Neanderthals at least twice, producing offspring whose descendants are present in living human populations outside Africa. We know that modern humans interbred with Denisovans, and that Denisovan ancestry is present in substantial concentrations in populations in Southeast Asia and Oceania. We know that Neanderthals and Denisovans interbred with each other. And we have genetic evidence suggesting that one or more additional archaic populations, unknown from the fossil record, known only from their genetic signatures and living genomes, also contributed to the modern human gene pool. The human genome is a palimpsest, a document written over by multiple hands, each new author writing over what came before without entirely erasing it. The traces of extinct species persist in living bodies, contributing in measurable ways to the immune function, the cold adaptation, the high-altitude physiology of their descendants. The boundaries between species, it turns out, were not walls. They were membranes. And the traffic across them was more frequent, and more consequential, than anyone had imagined. The development of the wheel, one of the most transformative mechanical inventions in human history, is often assumed to be among the most ancient of technologies. It is not. The wheel appears in the archaeological record approximately 5,500 years ago, in the region of Mesopotamia and the Eurasian steppe. This is thousands of years after the development of agriculture, writing, and complex urban civilization. Humans built the pyramids, organized empires, and developed sophisticated astronomical knowledge before they had the wheel. What made the wheel possible was not intellectual capacity humans had that in abundance for tens of thousands of years before it appeared, but the availability of draft animals capable of pulling wheeled vehicles. A wheel without an ox or a horse to pull it has limited utility. The domestication of horses and cattle, and the selective breeding of strong draft animals, was a prerequisite for the wheel to become a practical technology. Once available, the wheel transformed the movement of goods, the organization of armies, and the productivity of agriculture. Its consequences spread rapidly across the connected world of Eurasia. It did not reach the Americas before European contact, not because the indigenous peoples of the Americas lacked the cognitive capacity to invent it, but because they lacked the large draft animals that would have made it useful. Llamas cannot pull wheeled carts effectively. The technology was not available because the ecological prerequisite for it was absent. Invention does not happen in a vacuum. It happens at the intersection of cognitive capacity, accumulated knowledge, and ecological possibility. Change any one of those three things and the history of technology changes with it. The human capacity for music, for art, for story, for what we gather under the term culture is not, in the view of most evolutionary biologists, an accident or a luxury. The question of why these capacities exist, why natural selection produced creatures who paint cave walls and compose symphonies and tell stories around fires, has been approached from multiple directions. Darwin himself believed that music, specifically, might have evolved through sexual selection, that the capacity to produce musical sound was attractive to potential mates, in the same way that the peacock's tail is attractive, and that this attraction drove its development. Others have argued that cultural production is a direct consequence of intelligence, that brains large enough to do the practical things they evolved to do inevitably generate cultural behavior as a byproduct, in the same way that a large engine generates heat even when heat is not its purpose. Still others have argued that culture is adaptive in the most direct sense, that groups with richer cultural traditions survive better, cooperate better, transmit knowledge more effectively, and raise healthier children than groups with impoverished cultural traditions. All three accounts may be partially correct. What they share is the recognition that human culture is not a veneer on an otherwise animal nature. It is continuous with that nature, grown from it, shaped by the same processes, serving many of the same ultimate purposes, even when its proximate expression looks like nothing more than beauty for beauty's sake. The emergence of Homo sapiens coincided with a wave of large mammal extinctions across every continent that humans colonized. In Australia, within a few thousand years of human arrival approximately 65,000 years ago, the majority of the continent's megafauna, animals weighing more than 100 pounds, went extinct. Diprotodonts the size of hippopotamuses, marsupial lions, giant wombats, enormous flightless birds, all gone within a geologically brief period after the arrival of human hunters who had evolved in Africa alongside prey animals that had learned, over millions of years, to fear them. The Australian megafauna had not. They had no evolutionary experience of human hunters and no inherited behaviors of wariness. They were, by all accounts, easy to approach and easy to kill. The same pattern repeated in the Americas approximately 13,000 years ago, when the first humans arrived and the mammoths, mastodons, giant ground sloths, American horses, and camels disappeared within a few thousand years. In New Zealand, within centuries of Polynesian arrival approximately 700 years ago, the moa, a flightless bird standing 12 feet tall, was hunted to extinction. The human species has been the most consequential large predator in the history of life on Earth. The extinctions that followed human arrival on every new continent represent a permanent reshaping of the world's ecosystems. We did not know we were doing it. The animals we hunted did not know what we were. The encounter between a species with no experience of human predation and hunters who had been refining their techniques for hundreds of thousands of years had only one outcome. The human capacity for empathy, for feeling something of what another person feels, for being moved by another's pain or joy, has neurological correlates that suggest it is not simply a learned moral response but a built-in feature of the social brain. Mirror neurons, cells in the motor cortex that activate both when an action is performed and when the same action is observed in another individual, were first described in macaques in the 1990s and have since been studied extensively in humans. When you watch someone reach for an object, neurons in your motor cortex activate as if you were reaching for it yourself. When you watch someone experience pain, regions associated with pain processing in your own brain activate in response. This neural mirroring is believed to be the substrate of empathy, the mechanism by which human beings literally simulate the experiences of others, running internal models of what another person is going through rather than merely inferring it abstractly. The empathic response is not unlimited or unconditional. Research consistently finds that it is modulated by social context, by perceived group membership, by whether the person's suffering is seen as similar or different. The same neural mechanisms that produce empathy for in-group members can fail to activate for out-group members, a finding with obvious and disturbing implications for how empathy functions in intergroup conflict. Empathy is real. It is biological. And it is partial, in ways that require active effort to extend beyond its natural boundaries. The development of agriculture and settled life created, for the first time, the conditions for sustained, organized inequality. Hunter-gatherer societies are not perfectly egalitarian, dominance hierarchies exist, and some individuals have more status and access to resources than others. But the structural constraints on inequality in mobile societies are severe. You cannot accumulate more possessions than you can carry. You cannot build a permanent stockpile of food in a society that moves constantly. The differential between the most and least powerful member of a mobile band is constrained by the physics of nomadic life. Settled agricultural life removes these constraints. Food can be stored. Land can be owned. Surplus can be accumulated across years and generations. The differential between those who control the surplus and those who work to produce it can grow without limit, and across the archaeological record, it did. The skeletal record of early agricultural populations shows clear evidence of this inequality. Individuals buried with elaborate goods, copper ornaments, exotic shells, prestige weapons alongside individuals buried with nothing. Skeletal markers of chronic hard physical labor concentrated in certain individuals and absent in others. The biology of the body itself begins to record social position. The hierarchies that emerged with agriculture, the divisions between those who command and those who obey, between those who accumulate and those who produce, are not biological inevitabilities. They are the consequences of a specific economic transition. They have been with us for approximately 10,000 years, which is, in the context of the full span of human evolutionary history, a very short time. The human brain devotes an extraordinary proportion of its resources to the processing of faces, more than to any other single category of visual object. The fusiform face area, a region in the temporal lobe specialized for face processing, activates more strongly and reliably to faces than to any other stimulus. Damage to this area produces prosopagnosia, the inability to recognize faces, including the faces of family members and close friends, even while retaining the ability to recognize other objects normally. The deficit is specific to faces. A person with prosopagnosia can see a face perfectly well. They cannot recognize whose face it is. The degree of specialization for face processing in the human brain reflects the social demands of human life. In a species where a substantial portion of the critical information about another individual, their mood, their intentions, their identity, whether they are to be trusted, is read from their face, the ability to process and remember faces with high accuracy and speed is an enormous adaptive advantage. Human infants are preferentially attentive to faces within hours of birth, before they have had time to learn that faces are important. The preference appears to be innate. The brain arrives in the world already organized to pay special attention to the configuration of two eyes above a nose above a mouth. Every face you have ever found beautiful, threatening, familiar, or strange was processed through a system that evolution spent millions of years building specifically for that purpose. The recognition happens before thought. The reaction precedes the word for it. The relationship between humans and fire is so ancient and so intimate that some researchers have argued it should be understood not as a technology we use but as a relationship we depend on. The anthropologist Dennis Sangade has studied the fire-making evidence at Neanderthal sites and found that fire use appears to correlate with climate. Neanderthals made fires more reliably during cold periods and less reliably during warm ones. This suggests that Neanderthal fire use may have been opportunistic, making fire when they could or needed to rather than the habitual, continuous fire maintenance that characterizes modern humans. Modern humans, by contrast, appear to maintain fire virtually continuously in every culture, in every climate, in every context. The fire is kept going not only when it is needed for warmth or cooking but at all times, as a constant presence, a permanent feature of the inhabited space. This continuous fire maintenance may reflect the degree to which the human body and the human way of life have become genuinely dependent on fire rather than merely benefiting from it. A human being dropped into a cold environment without fire is not merely inconvenienced. They are in serious danger, in a way that a healthy chimpanzee in the same environment is not. We have traded cold tolerance for cooking efficiency, fur for fire, the biological capacity to survive without warmth for the cultural capacity to always produce it. We are the only species that cannot fully survive without a technology. The fire made us. We cannot now exist without it. The archaeological record of the last 300,000 years contains growing evidence that Homo sapiens was, from very early in its existence, a species capable of abstract and symbolic thinking long before the Upper Paleolithic revolution that was once thought to mark the beginning of fully modern behavior. At Blombos Cave in South Africa, archaeologists have found engraved geometric patterns on ochre dating to approximately 75,000 years ago. Perforated shell beads from the same period and from sites in North Africa suggest the use of personal ornament, symbolic communication of identity, at similarly early dates. A piece of ochre from another South African site, dated to approximately 100,000 years ago, bears what appears to be a deliberately engraved crosshatch pattern. These finds do not suggest a sudden cognitive revolution. They suggest a long, gradual development of symbolic capacity, manifesting in scattered and impermanent ways across a wide geographic area, for tens of thousands of years before it became the constant, elaborate, continent-wide phenomenon visible in the European Upper Paleolithic. The human mind that produced Lascaux was not born 45,000 years ago. It was the mature expression of a capacity that had been developing, quietly, incompletely, sporadically, for at least 150,000 years before that. The cave paintings were not the beginning. They were the moment when the beginning finally became fully visible. The question of consciousness, of why and how the physical processes of the brain give rise to subjective experience, to the sense of there being something it is like to be alive, is sometimes called the hard problem of consciousness, and it remains one of the most genuinely unresolved questions in all of science. We can describe the neural correlates of consciousness, the brain states associated with wakefulness, with attention, with various subjective experiences. We can trace the evolution of the brain structures associated with conscious experience. We can describe, in significant detail, what the brain does when a person is conscious. What we cannot explain is why any of this should be accompanied by experience, why there should be something it is like to see red, to feel pain, to hear music, rather than simply the electrochemical processes that underlie these experiences occurring in the dark, without any inner light? This question may be the deepest one the story of human origins opens. Everything else in this story, the fossils, the tools, the migrations, the DNA, describes the outside of the process. It describes what happened to the body, to the population, to the species. The hard problem asks what was happening inside. Whether there was something it was like to be an early hominin standing on an African grassland 3 million years ago, looking up at the stars. Whether that inner light was always on, or whether it was gradually kindled over millions of years of neural development, or whether it arrived all at once at some threshold we cannot identify. We do not know. The question is open. And it may be the most important question that the species capable of asking it has ever asked itself. The last fact is not about a discovery or a fossil or a gene. It is about the act of looking. At some point in the deep past, we cannot say exactly when, and it does not matter exactly when a hominin stood in an open landscape and looked up. Not for any practical reason. Not to track prey or watch for predators or monitor the weather. Simply to look. To take in the sky, the stars, the darkness between them, and to feel, for the first time, or for the 1000th time, that something was there that the looking could not fully reach. This moment, the moment of curiosity without immediate purpose, of attention extended beyond what survival requires, may be the single most human moment in the entire story. The tools and the fire and the language all serve survival. But the looking at the sky for no reason, the wondering without any expectation of an answer, the sense that the world contains more than can be used or eaten or explained, this is the beginning of something that has no survival value and yet has been with us since the beginning. Every science, every philosophy, every religion begins here. Every attempt to understand where we came from, including this one, is a continuation of that first upward look. The question is the same. The sky is the same. The darkness between the stars has not changed. What has changed is the creature looking up, the creature that now has 300,000 years of its own history to look back through, and millions of years of ancestral history before that, and the knowledge, hard-won over centuries of inquiry, of what it is and where it came from. You are that creature. You have always been looking up. And the looking, in the end, is the most human thing about you. Somewhere in sub-Saharan Africa, 6 or 7 million years ago, a creature moved through a landscape that no longer exists. It walked on 2 legs, or on 4, or somewhere in between. It had no language and no fire and no understanding of what it was or what it would become. The sky above it was the same sky. The stars were the same stars. The darkness between them was the same darkness. That creature is your ancestor. Between that moment and this one lies everything told tonight, the bones in the caves, the tools in the river sediment, the DNA extracted from fragments of ancient finger bone, the hand stencil on the cave wall, the first city in the river valley, the canoe crossing the open Pacific. The endless migrations, the extinctions barely survived, the encounters with other kinds of being who were almost us but not quite, whose traces now live in fractions of your genome. You are the result of 6 million years of unlikely survival. Every extinction that did not take your lineage, every disease survived, every migration that succeeded, every winter endured with fire, all of it necessary, none of it guaranteed, the entire chain unbroken from that first upright step to this present moment. The hand you could raise right now is the hand that pressed itself against a cave wall 45,000 years ago in Indonesia and left a mark that said, "I was here." The brain behind your eyes is the brain that looked up at the stars and felt, for the first time, that they required an answer. You carry all of this. It is not metaphor. It is in the cells of your body, in the architecture of your mind, in the face you show the world, in the dreams you have in the dark. You are very old. You are the newest thing on earth. You are 6 million years of survival distilled into a single body, lying somewhere quiet, breathing slowly, at the edge of sleep. The story goes on. It has always gone on. And you are, in this moment and every other, exactly where it has been heading all along. Sleep well.